This time on Andy's Motorcycle Obsessions, I'd like to talk about exhaust systems. Really? No, they don't. It's a wide misconception, actually. If anyone says that to you, you need to forget about everything they've just told you and then probably ignore everything that they tell you from that point on, because back pressure is bad always. So I think it's important to understand when we're talking about exhaust systems where the exhaust actually starts and what's happening inside the combustion chamber. Now, I'm dealing primarily here with four-stroke engines. So as the name suggests, there's four strokes to one operation. So an engine is a cyclic machine. It will just do the same thing over and over and over again. It will do it at varying RPMs, revs per minute, but it's going to be doing the same thing. We start with our intake stroke. So the piston is heading down and it's creating a pressure differential. Now it's another misconception that engines suck air in. They don't suck air in. What they do, the piston pulls down in the cylinder, and it creates a very low pressure or vacuum condition. And Mother Nature hates that, so it just tries to equalise. So the air on the outside rushes in to the cylinder, and there's a few things that are stopping it. First thing is an air filter, then there's a carburetor, and in the carburetor we actually accelerate the air through a venturi to create a pressure differential to draw fuel from a fuel bowl and blend it into the air mix. And pistons oscillate. They're not a constant speed. So as the piston approaches around the middle of the stroke, it's going at its fastest, and then at bottom dead center and at top dead center it actually stops. So if you were to draw a graphical representation, it would look something like that. So the piston speeds up as it hits the middle of the stroke, and then it slows down as it gets to the bottom. Engines run on air. They don't run on fuel, they run on air. What we do is we actually burn a bit of fuel to heat the air up. So the fresh air is drawn in by pressure differential, passes through all that process in there and tries to fill the chamber. And depending on the type of camshaft, the size of the valve, the size of the piston, the length of the stroke, the shrouding around the valve, will have an impact on what they call the volumetric efficiency. Now you can imagine if you were to turn this by hand and let the piston come all the way down to the bottom, it will equalise 100%, and that is 100% volumetric efficiency. Start speeding things up, however, and it gets a little trickier. So, peak RPMs, you're not going to be getting 100% of the air into that cylinder. But it does the best it can, and you can improve that with carburation, intake, cylinder head design, camshafts, porting and polishing, etc. Anyway, back to the exhaust. So we've drawn all that air in via pressure differential, and the chamber is now filled with air, which is 21% oxygen on a good day at sea level. And the reason they talk about sea level is because altitude will have an impact. There's two different types of pressures. There is absolute pressure and there is gauge pressure. Generally in engineering we talk about absolute in these types of applications. So when we're standing at sea level, we've got about 15 psi in the air around us. But of course, if you were to hold a gauge up, it would just read 0 because the gauge has been calibrated to that point. We squash all that air up because it does compress, and then we fire a spark and we ignite that fuel, and it rapidly heats that air, and air just expands very, very quickly, and that force is what drives the piston back down. So the piston is driven down to the bottom of the stroke, and at this point we want to start thinking about opening up that exhaust valve. The rotating mass continues to drive the piston back up, and of course the camshaft opens the exhaust valve, and this is the first opportunity here for scavenging. What we can do is, as it approaches the top of its stroke, we can open the inlet valve, because you're going to have a pressure differential here now. It's going to have largely escaped out of the exhaust port, hopefully with velocity, drawing the gas out with it. And if we open the inlet valve late in the exhaust stroke, what we can do is start flushing fresh air through the cylinder to get rid of all of those impurities out the exhaust pipe. So I mentioned scavenging. What is scavenging? Essentially what we're trying to achieve is trying to help draw those gases out of the cylinders by using the pulses from the other cylinders. If you can imagine on a racetrack, a circuit racetrack like NASCAR or Formula One or our V8 supercars here, most forms of motorsport, MotoGP, they will do a manoeuvre that is known as drafting, where you have one vehicle that's pushing through the air, and as it pushes through the air, the velocity creates a negative pressure area behind the car. So by getting your bumper bar right up on their bumper bar, you actually can achieve the same speed with less of an input. And that's what we're trying to do with scavenging. So I mentioned that the first scavenging event happens in the exhaust port when the valve first opens. And where we're trying to achieve that scavenging is with the primary pipe. We need to get that exhaust out of that cylinder as fast as we possibly can. Now, there's a delicate balance between flow and velocity. So what people, I think, mistakenly think is, all right, we'll just put a bigger primary pipe on there, bigger pipe, so the gas has got more room to go. The problem with that is that it slows the gas down, because we know from looking at Venturis, if you've got a pipe that we put through a Venturi, gas or fluid that we put through a Venturi, where the pipe is narrower in diameter, it has to speed up, it has to accelerate to get through there. So what we actually want to do is try and replicate that. But of course it'll slow down when it gets into a bigger pipe, and that will cause back pressure. So you put a bigger pipe on it and you'll lose all your torque, because you won't be getting all of those fumes out of the cylinder, and the incoming air charge will be polluted by the residual exhaust fumes. So what you want to try and do, imagine if this is your exhaust port, you've got your valve coming through here, where it interfaces with the primary pipe, you really want to try and match that size for size, to be honest. So that helps to promote laminar flow, so it's not crashing into the edges of the pipe or gaskets, etc., and bouncing around. You want to try and produce laminar flow, and you want to try and balance between restriction, so you don't want to go too small, but you also want to maintain velocity, so you want to go small enough, and small enough is generally the size of the port. Now, in an ideal world, you would try and get that exhaust to travel out of the cylinder in a straight line as far as you possibly can, which is why on drag cars you see they have those big zoomies where they come in straight out of their head and then up and gone. That's not practical. Most motor cars are a real pain in the bum, because they've got things like steering boxes and chassis rails and suspension components to try and fit your exhaust pipe around. So from a packaging perspective, they're very difficult. Motorcycles were not as restricted, but we still have to get the exhaust to the back of the bike. So what you want to see if you're looking at purchasing a pipe is that, one, the primary tubes aren't oversized, two, that they go as straight as they possibly can, and then gentle curves where possible, and start to bring the exhaust to the back of the bike. So our first scavenging event happens in the primary tube. Our second scavenging event will then happen in the collector. Pretty well all exhaust systems are designed for scavenging, and will have some sort of a union of the pipes. Yeah, all right, shut up. They don't work. All they do is make noise. But yeah, so let's have a look at what they did with the XS 1100. They came out of the cylinder head with the primary pipes, and then they came down, followed the line of the chassis, and went underneath, and they joined in a collector underneath. On the XS11, there's 4 pipes that went into two 2-into-1s, and then exited the back of the bike. So looking at it, got your primary pipes like so, and they came down underneath the chassis and they joined into one. So this collection point here is another scavenging point. And the thing is that when you hear people talk about tuned pipes, tuned length pipes, a lot of people believe that means that all the primary pipes are exactly the same length. Yes, that's true. You want to try and get the primary pipes to be as close as possible to the same length, so that the exhaust pulses are all travelling the same distance in the same amount of time. But tuned length is actually just talking about the relationship of the collector in terms of its proximity to the exhaust port. So the engineers need to work out how many degrees of crankshaft rotation is it going to take at a certain RPM range for that pulse to reach the collector and create a negative pressure wave in the other pipe. And it needs to be matched as best as possible to the torque power curve of your engine at a particular RPM. So exhausts are not active, they're a passive system. Some mufflers are active mufflers in terms of noise control, and I'll talk a bit about that later. But exhaust systems are a passive thing. They're a set length, they don't vary in length depending on RPMs. So the closer that collector is to the cylinder head, the lower in the RPM range it's going to have an effect, because it's less time for the exhaust pulse to reach it. So what happens in a collector or a wide pipe? You've got 2 pipes coming together. Now this is where we start to get into secondary pipe sizing. You need to understand what CFM is going to be flowing through your pipe, and make sure that the pipe can handle peak RPM CFM flow. Otherwise you create a restriction which creates back pressure. So again, it's that balancing act between velocity and flow, and we need to maintain velocity at all times, but also try and make sure that it's big enough that it can still flow adequately. So the exhaust pulse comes down, it'll reach this section here and open up, and that, as it passes this point here, so your exhaust pulse coming through here from this direction, it creates a negative pressure behind it, and hopefully if everything's timed right in terms of the distance, the length of the pipe, as this pulse arrives from this side, it'll be entering that negative pressure area and help draw the gas through. So that's what's happening in a collector or a scavenging system. Right, so getting back to the XS11 design, we've got our 2 primary pipes into a collector either side, and then they exit the back of the bike. But in between that is an H pipe. And an H pipe, some people call them a balanced pipe. They're not really a balanced pipe. What they are is another scavenging event. So we have another opportunity here to create a lower pressure and help draw the gases on the other side. And this is at a higher RPM range because it's further from the cylinder head. So the XS11 pipe actually has 3 scavenging events. There's the one in the cylinder chamber, there's the one at the first set of collectors, and then there's one at the H pipe, and again also probably in the muffler as well. So it's designed to have a much broader spread of torque compared to, say, a 4-into-1, which only has a single collection point. And it's generally sort of in that mid-range to high RPM. It's more designed for straight line speed. You won't have as much torque coming out of the corners at low RPMs as you will with a pipe design like this, where you've got a nice short run to to a collector for a scavenging point, and then a high RPM scavenging point further back. Some exhaust systems, including my Ducati, have a crossover pipe where the pipes come together like so. So the exhaust will actually follow at low RPMs, will sort of dissipate into here and split off into either side. But as the RPMs pick up, it'll actually follow around here with its pulse, creating a negative pressure and drawing the one beside it. That's what X pipes are about. And on Ducatis, they're flattened right out. They're like a Venturi, and they really help to accelerate that exhaust gas. So yeah, so 4-into-1s, you'll have a bank of 4 coming out of your exhaust, and these pipes should all be roughly an even size, however the configuration in terms of length, and they'll all come together in one collector and then out towards the muffler. So the position of that collector is critical in terms of where it's going to operate in the RPM range. And also the length of the pipe on the back of the collector will have an impact as well as you reduce down to your muffler size. So speaking about mufflers, there's 2 different types. There's active and there's passive. Most motorcycles have a passive muffler or an absorption muffler, where you'll see a length of pipe that's perforated. So it's got all these holes in it. And those perforations can be about 30% of the total surface area of the pipe. And then surrounding that, they have so you've got your gas coming in here. They have absorption material in there, like the fiberglass bats and soundproofing stuff that they put in your roofs, insulation. And the whole theory here is that at low or steady RPM range, the gases and the pulse waves actually come up through these holes and bounce around in here and come back out again. So it quietens it all down. But then as the RPM increases, what you find happening in there is that these gases actually become trapped in here, and it builds up pressure, and it just flows straight through, which is why you can be cruising on it. If you've removed your baffle, which creates back pressure, if you remove your baffle from here, what you can find is that at steady RPMs, sort of highway speeds around town, you can have a fairly quiet bike. But as soon as you start cranking that throttle on, it really gets raspy and starts to get loud, because the absorption material is doing what it's supposed to do, and that is to stop absorbing that noise and just allow the gas to exit the bike at the high RPMs. Active mufflers will have an inlet and an outlet, and usually something in the way, whether it's some sort of baffling. It might have chambers in there where it allows, these are like reverberation chambers, so what it does is it basically puts a counter energy wave, bounces it back and tries to cancel out the sound wave coming in, a bit like noise cancelling headphones, where you've got the battery that you need to, basically like a speaker, that counters the sound waves with other sound waves and cancels each other out. That's what they call an active muffler. Alright, so I thought I'd wrap that up. I've got 3 bikes that I own, and they all have different exhaust systems on them. The XS1100 I've got has got a 4-into-1 with a short absorption muffler in it, free flowing, no baffle. The Ducati has a 2-into-2 with a crossover pipe, and also has absorption mufflers with no baffles in them. And my CB450 is the factory standard twin pipe, twin absorption muffler. And they all work, they all have their function, but I think you just got to be careful, because there is a science behind mufflers. I think it's important to point that out, and that exhaust systems have a science, and engineers design them based on they're doing calculations on pulses that are travelling 1100 feet per second at the speed of sound, and trying to time that that scavenging event to happen precisely in the right range for the peak torque of that motor. So they'll look at where the motor develops its peak torque, what RPM is that, right, let's see how many degrees of crankshaft rotation it's going to take at that RPM to get the pulse down. So there's a bit more to it than just banging some pipes together in your shed. I hope it was helpful to someone out there and help maybe make the right choice when you're going out looking for an aftermarket exhaust, or modifying or manufacturing your own. It pays to go and do your research and have a look into the formulas that are available to pretty well anyone who wants to go looking online for them, or look for somebody who has made a known reputable aftermarket exhaust for a particular bike. Well, thanks for tuning in. I hope you enjoyed that. Don't forget to stay tuned and like, subscribe and comment. And you can go and find us on Facebook now at Andy's Motorcycle Obsessions. And I'll catch you next time. Bye for now.